I made some discoveries about the Mobius strip. Are you interested?
Sure, but what's a Mobius strip?
You make a Mobius strip by taking a strip of paper and forming a loop, but then you add a half twist to it. This then forms a surface with only one side and only one boundary component. The Mobius strip has the mathematical property of being non-orientable.
What does non-orientable mean exactly?
In mathematics, orientability is a property of surfaces in Euclidean space measuring whether or not it is possible to make a consistent choice of surface normal vector at every point. A choice of surface normal allows one to use the right-hand rule to define a clockwise direction of loops in a surface. More generally, orientability of an abstract surface, or manifold, measures whether one can consistently choose a clockwise orientation for all loops in the manifold. Equivalently, a surface is orientable if a two-dimensional figure such as in the space cannot be moved continuously around the space and back to where it started so that it looks like its own mirror image.
Look, love. I'm blonde. Can you make that more simple to understand, please?
Yes, I just mean that because we've connected edge A to edge B, they become the same edge and therefore the surface becomes one continuous surface. The Mobius strip has several curious properties. A line drawn down the middle will meet back at the seam but at the other side. If continued, the line will meet the back at the starting point, so effectively we've gone nowhere. This line will be double the length of the original strip. This single continuous curve demonstrates that the Mobius strip has only one boundary. Boundary means side.
I see. Before you added the half twist, the loop of paper could sit on the table. There was a lower edge and an upper edge, and there was an inside boundary and an outside boundary. But when you connected the edges together with one twist, we lost an edge and one boundary. Is that correct?
Yes. Now here is where it gets weird. What do you think happens when we cut it down the middle? Our scissors start where our pen started, we cut and we cut, then end back at the starting point.
We've cut it in half, right?
Do we have two separate pieces?
Yes.
No, you were wrong. Cutting a Mobius strip along the center line yields one long strip with two full twists in it, rather than two separate strips. The result is not a Mobius strip. This happens because the original strip only has one edge which is twice as long as the original strip. Cutting creates a second independent edge, half of which was on each side of the scissors.
I don't understand. We started with one half twist in the loop, now we end up with two full twists, as in 4 half twists. How is that possible?
That is simple. The equation for the number of half twists after cutting a Mobius strip down the middle is 2n plus 2 equals m, where n is the number of half twists before, and m is the number of twists after cutting a Mobius strip down the middle. Do you understand so far?
Yes, I'm not that blonde. I can do simple algebra. 2 times 1 twist is 2, plus 2 is equal to 4 twists. After making the cut, we have a manifold that has 4 twists, 2 edges and 2 surfaces, or boundaries.
That's correct. Adding the cut adds a new edge which also adds another boundary.
Do what happens if we cut this new strip down the middle? Do we still have one piece?
Can you guess? Do we have one piece, or two separate pieces?
I have no idea what the result is. This topology is hurting my little brain.
Cutting this new, longer, strip down the middle creates two loops, one is linked into the other and each has 4 half twists. This time we get 2 separate pieces which are identical and linked by the middle.
Is there another way that we can get the one flip Mobius strip?
Yes. If the strip is cut along about 1/3 of the way in from the edge, it creates 2 separate strips. One is a thin original Mobius strip. It is the center third of the original Mobius strip and comprises 1/3 of the original width. It is the same length as the original strip. The other separate strip is twice as long as the first but is the same width. It has 4 half twists, 2 boundaries and 2 edges.
How is this possible?
The middle 1/3 never received an extra edge when we made the cut. So it stayed the same but just got more narrow. It was the longer loop that reshived the extra edge. So it was the same as cutting the Mobius down the middle, except we ended up with a stripe that was 1/3 the original width and just 1/2 the width.
That is simple so far. All of this is known topology. What about your discovery?
Yes, I'll get to that now, but we leave topology and go into graph theory and knot theory. Are you ready for that?
Ready as I'll ever be.
Okay. I've cut the 1-1 Mobius strip down the middle, then taken the resulting manifold with 4 half twists and transformed them into knots.
How?
First, I let the strip cross over itself, then I added a half snip into the paper on each half where the two edges meet. This allows the planes to cross each other. It only takes 2 crosses to cancel all the twists in the original 4-twist manifold. One intersection cancels 2 twists. This is called a framed knot. Next, I drew the knot diagram, and it just so happened that there were 5 different knots. All had 2 nodes and 4 edges.
You've kind of lost me now. I can't visualize what one of these knot diagrams looks like.
It's simple. The easiest one to explain is just a knot. Imagine looking down on a table at a piece of string that is just in a circle with 2 loops on themselves. We come down anti-clockwise, turning right, turn a full 360 degree into a smaller loop also anti-clockwise, then go under the string where we cross it and head up, now turning left before we make another smaller 360 degree turn. Again go under the string where we cross it and head back down to hit the starting point again. The knot notation is then +1, -1, +2, -2. Have I lost you?
Listen, mate. I'm no dumb blonde, okay? I know what you are saying. If we ignore the knot notation, which just accounts for the over and under arrangement, and just think about the graph that you are describing, it is a simple graph that is a Hamiltonian path.
Yes, but the problem gets more complex when we use a 3-flip Mobius strip.